Hello everyone, welcome to the demonstration corner. Today we're going to talk about the TPS-2, the Transient Plane Source 2. We always do a little quick introduction to the demonstration corner, and this part of the demonstration corner actually shows a nice capture of our portable series, our HFM25 guarded heat flow meter, portable transient hot wire L2, our portable series of transient line source, transient hot wire, and transient plane source. So these are all aimed at the economical market. And then our heat flow meter, our transient hot wire, guarded heat flow meter, and MP1. So we'll just turn the camera and just show you what's in our demonstration corner and that it's always available. So down here is our MP2, which combines asymmetric or single-sided TPS sensor, transient hot wire sensor, and transient line source sensors for primary measurements for each of those applications. That's a really smart tool that allows you to enter into the thermal conductivity market in an economical way. This is our THW L1, or transient hot wire for liquids. This is able, depending on the model, to test from cryogenic temperatures up to 300 Celsius. The key capability is that you can also back pressure up to about 20 or 35 bar, which allows you to test past boiling points. We will talk about the TPS-2 in a second, but just to complete the loop, this is our MP1, which combines the two instruments that we just showed, which are transient plane source method and transient hot wire method. And the new addition to this is the transient line source method, with a whole bunch of new capabilities. Thermal conductivity range up to 1800 watts per Kelvin, pressure, temperature, and many new modules that make this the marquee transient method in the industry. Circling a little further is our guarded heat flow meter following ASTM E1530. This is for measuring complex layers and structures. It has very unique capability that if your materials are not repeating in layering, this has the ability to measure very complex materials in a conductivity range between plastics around 0.1 up to 100 watts per Kelvin and up to 300 degrees Celsius. And then lastly is our heat flow meter following ASTM C518 and associated standards, international standards. This is designed for measuring insulation and construction materials. It measures thermal resistance and thermal conductivity. This is one size. This is 300 by 300 by 100 millimeter max interior. We have a 200 millimeter by 200 millimeter, and then the HFM25, which is part of our portable series. So coming back to our TPS-2, this is our basic expanded transient plane source TPS-2 following ISO 22007 2-2. I think I got that right. And today we're going to demonstrate on the measurement of Pyroceram 9606. We're going to set it up for symmetric, so two-sided. The theory of the method is that your sensor is sandwiched between two pieces of the same material. You could, of course, run these measurements asymmetrically or single-sided. And in a future video, that's certainly something we will show. And I'll show you the basic configuration of that. It works exactly the same. The unit itself, the range is, there's two thermal conductivity ranges on the instrument that are optional. The basic range is 0.01 to 100 watts per Kelvin. And then the max range is 0.01 to 500 watts per Kelvin. It has the industry modules for SLAB for measuring conductive sheets, thin film, and anisotropic materials for measuring directional or anisotropic materials that have, due to fillers or layers, have anisotropy, and lastly for measuring bulk properties. Ideally, it's best suited for solids, pastes, and powders, or a range of liquids. Of course, transient hot wire is more ideal because of its primary use in design or to limit the effects of convection, although there is a liquid cell for this. There is temperature capability, but the basic system setup as it is here is for benchtop testing. We'll show you the setup and the software in that. Tomorrow, at the same time, we'll be demonstrating the temperature add-on you can add to this to allow you to test different ranges. So we'll talk about one option. There are, of course, more options, and we'll review that and get into some measurements tomorrow. So I'm going to switch to camera number 2, and which will give you a close-up of the sample setup, sensor setup, and the sample setup. and walk you through that, and then we'll share the software. So you should be able to see our basic room temperature sample holder. This is a sensor adapter. So on the bottom, in this sensor that we're reviewing right now, is a 12.8 millimeters. You can see there's 4 contact points. These 4 contact points are what we're going to make when we insert it into the adapter and affix the sensor. So that creates the electrical contact. This sample holder and that adapter are auto-recognized by the TPS-2, so it knows what's connected to it in terms of the adapter. You can this particular adapter is good from minus 75 to 60 Celsius. We have a peak version of the same thing with different cabling, peak being a high temperature plastic that allows this sample holder, the same sample holder, to be used up to 300 degrees Celsius. So I'm going to insert the sensor with contacts down, and of course your camera angle, you're not going to be able to see it, but you can see the first 2 electrical contacts. There are 2 in the back of that, and there's a framed in box that as I back these knurled knobs off, you can see that being lifted. Now again, the camera angle doesn't allow you to see that, but it tells you precisely where to place that. And typically for affixing it, we just put your finger in the middle and spin these until they stop naturally, and then just do half a turn. That's plenty of contact to create the electrical connection. So for setting up the sample, here is our 2 pieces of Pyroceram, 9606. These are well defined, well known. There's lots of publications on what the thermal physical properties of these are. I already measured the dimensions. We will need that for inputting into the software. So for doing asymmetric test, so if I only had 1 piece, I would use the included piece of known insulation and lower the sensor. So when we have different thicknesses of material, we use the sensor adapter travel to accommodate different dimensions. So that total travel is, each side is more than 50 millimeters. So your total sample could be, each half could be more than 50 millimeters, and the dimensions this way are more than 100 millimeters. So for an asymmetric test, my configuration would be like that. Known material on the bottom, the software allows you to select what material that is, and your unknown on the top. Of course, you could reverse that. This is convenient this way. But if you have 2 of the same material, which is the ideal situation, you would put your sample half on the bottom, center it as best you can, and lower the sensor so that it sits in the center, and then place your second piece on top. Now what we're going to do is use the included metal protection so that we don't scar our material with the force we're going to apply. So when we lower the top bar, there are graduated holes that make sure that we don't get any drift when we apply pressure. So they're spring loaded, so we pull on these and we lower that till it gets to the sample height. And then for fine tuning, to apply the final pressure, we just turn that knurled knob a little bit. So you get large adjustment and fine adjustment. So for doing the bench top in our lab, this is fine. If you wanted to do chamber measurements, you would put this in a chamber, or you would use the device we're going to talk about tomorrow for controlling temperature. So that's our setup. Everything's good. And I'm going to change the camera to our desktop, or change the video rather to our desktop, so you can see what software we're looking at. So this is the basic software for doing data acquisition. So there's 2 applications that come with every TPS-2 or MP1. And we've separated the collection of data, or what we call data application, into 1 application, and the analysis of the data generated into our analysis application. Why did we do that? Because it gives us a lot more control and less confusion about trying to stuff a lot of data and calculation into 1 screen. So it really allows us to separate out that. So of course, the other advantage to that is you can put the analysis software on another computer if you want, and conveniently make those calculations away from the instrument. So today we're going to make a symmetric measurement. Again, you can do asymmetric, which would be single-sided. These are the options that you can add to the instrument. We're going to do isotropic measurement. Anisotropic is for measuring directional properties. So if you have a material that has a defined structure that creates anisotropy, you can use that to separate out radial and axial values. We're going to do semi-infinite body, so that would be a bulk measurement. Slab would be an add-on which measures thin conductive sheets. Thin film is for measuring thin materials in the range of 0.01 to about 1 millimeter thick. So again, we're going to do symmetric, isotropic, semi-infinite body, and not thin film. Here, you place the name of your operator. I just put user. Here you would point to where you want the data saved, and you would click next, and that takes you to what devices is detected by the software. This is the device that is connected, which is the TPS-2. It is now only the room temperature sensor connected. How do we know? How does it know that? So if I go back to home, it shows the 2 connected devices. So it always knows what's connected to it. And tomorrow when we talk about this, you'll see that it auto recognizes the temperature devices as well. So if we go back here, we can, as we leave, we can go back to the same place. So it's room temperature, sample holder. So I click next, and I'm going to input the name. My height of that sample is 15 millimeters, and the radius is 25. Why is that important? First, I'm going to select the port. Why we have this option here is because on the MP1, it has multi-port for handling multiple sensors at the same time. The TPS-2 has 1 port. So here's where a part of our automation, which is selection of sensor. So using the theory that's understood that we can manually train you on, it knows that, and it selects the best sensor to fit your sample and satisfy all the experimental conditions. So if I click that, it shows 33171, which is 6.4 millimeters radius. If you want to see the difference, if my sample was 10 millimeters tall, or let's say 5, based off the diffusivity, it would select the appropriate sensor to satisfy experimental conditions based off that dimension. So if we go back to 15 millimeters, you can also manually select, of course, but we'll leave it based off the recommended. Here we're going to check our resistance. What that does is it verifies that I made good electrical contact with the instrument. It gives you a green symbol of pass if you had the wrong sensor selected, meaning instead of 33171, which was recommended, if I put in a sensor with a different resistance, it would warn you. Or if I had an open circuit because I didn't make electrical contact, it would warn you. Here's where we can input the temperature of the room. If this is connected to a temperature device, it pulls the temperature from that device. Now we come to our iTPS, which is quite an advantageous capability. Here we're going to select any number of ranges, and what it's going to do is it's going to automatically do a measurement, pulse in a very unique way to recommend the parameters. So in this material, if you mouse over it, it says ceramics and low conductivity, below 10 watts per Kelvin, which this material is. And then when we click iTPS, it's going to do a very specific set of functions. It's going to, based off that conductivity range, it has a total time, in this case, of about 150 seconds, that it will make a continuous measurement and then continuously dump that data to the software for analysis and look for the best time that satisfies specific parameters. One is the penetration depth, so we don't want the heat to leave the boundaries of the sample because our sample is a semi-infinite body. So it automatically knows because we gave it the dimensions. It's going to look for the optimum temperature rise and time to satisfy and then best fit. So the output of this will be a automatic selection of time and power. So we're not calibrating any of this. This is absolute method, which means from the raw output, we are calculating, the software is automatically calculating the thermal physical properties. So this is using the advantages of software knowledge and an experimental measurement to run that, what we call iTPS. I stands for the intelligence. That's really a big exercise and activity for us, was to create, advance this method in terms of intelligence, which of course creates better opportunities to generate good data. So while that's running, and this will take 150 seconds, so just over 2 minutes, and then we can go in and run a quick measurement, set up an experiment, and show the schedule what it looks like. So once this is complete, I'll come back to it, but I can show you what the data looks like on a couple different times, because for every material, there could be more than one test time. So we've gone ahead, and this is our transient analysis or analysis software. So I've opened up 2 experiment sets, one at 10 seconds, one at 20 seconds, and selected both of them. So as you can see, you can select one range of time, or you can open up more than one calculation, more than one rather experiment, in review, all of it. And then from here, you can export to Excel. Everything is pushed. Another unique capability is the ability to add multiple calculations to the same screen. So you're not calculating over your previous data, you're adding a new one. Why is that important? Because it helps you don't have to remember the past experimental results. So from this measurement, we get conductivity, thermal diffusivity, and volumetric specific heat. You can see the repeatability. Why are 2 test times appropriate in this material? Is because we have enough material that we're staying within the dimensions of the sample. So thermal conductivity for a homogeneous material is not time sensitive as long as you're not penetrating past the boundaries. So more than 1 time could be appropriate as long as you're staying within the boundaries. So we have 2 times, that's where the results are very similar. So an average of all of them, 2 different times, each one measured at 5 repetition, and then to the right of that you have the average conductivity for each series. So going back to data acquisition, we're still running that measurement. So from here I can demonstrate a few things. So let's say of this experimental set, I define 20 seconds as the important data. I can call that important, so when I open it up, it highlights that as data. Additionally, inside of the analysis, I can investigate the residual pattern, which means it tells you the quality of the fitting. I can see the temperature rise versus time raw data, the drift. So in advance of every measurement, it records 40 seconds of resistance at the sensor level to make sure that your conditions of sample and sensor are isothermal. This is all at 23 degrees, so there's no thermal conductivity temperature data to share. It's just all at the same temperature. And then your residuals and bulk property. So let's go back to that. So here we've completed our automation. You can see that these little gaps. So this is a continuous transient, but the little gaps are the data that's being pulled out of the data acquisition and represented in the software, continuously calculating. So it's not waiting till the very end, and it's not running individual times. It's running one long time, and from the very long time, recommending the best parameters that fit. So it's super intelligent in the sense that in one sweep of time, it can detect any number of conductivities and dimensions. That's really important. So by clicking close, you can see that it puts that time and power, which you can manually change if you want, but that's the automation, and we can run a quick transient. So a quick transient is a step before you set up a multiple measurement schedule. So I can run a quick transient. This quick transient function does not run the drift measurement because it's meant to be just a step before you measure schedule. So it will balance the bridge as per the ISO internally, and then you can see from the event log what it's doing. It will be supplying power to the sensor for the already defined time of 10 seconds and the power that it suggested. So we'll watch this, and then we'll have our quick transient parameters. So you don't really have to do it. It's just a nice step that if you want to make verifying measurements, you can do that. So here's our transients. Our transient, I should say, finished test, it's analyzing, so we can go to our quality indicators. There's no red, there's no identifying areas of concern. We've met all the quality indicators. And here's our residuals. You have good fitting, so I can click OK and go to next, which is our schedule. Here you can see the parameters that were measured for us and suggested. I can make, because these are ideal parameters, I can make a measurement of 5 or whatever number with the power that it suggested. There's a delay of 10 minutes default, which we suggest. Why? Is because we're raising the temperature of each measurement by 1 or 2 degrees. We want to make sure that dissipates. By clicking start, it will make 5 measurements with a 10-minute delay. Now, if you want to make more complex schedule, you can go into this function, and it'll allow you to do a range of powers and a range of times all automatically and build the schedule for you. Super powerful. By clicking start, it will build our data acquisition screen that shares the multiple measurement steps. So from here, we'll have a series of events in the event log going through and making all these measurements. And from here, as we progress through and this data becomes generated, we can see the raw data and transients on the left side, and it'll populate the full screen. And then by clicking this button or this button, it opens up our transient analysis, and we can look at our data like this. And you can look at data incrementally, or you can look at it after completion of the measurement. So in data acquisition, we see the data and the results with temperature, but if you want to fine tune those or run calculations, you can do that fully inside of thermal analysis. So that's it for today. Tomorrow we'll talk about the same capabilities. We're going to make some measurements on a material with temperature using our new thermal electric dry bath designed for the TPS-2, which goes from 0 to 100 degrees. We'll review some data and do more conversations. Thank you, everybody. If there's any questions, you can put it in the chat, or you can email us at info@thermtest, and we're happy to have further conversations.